Hello everybody, this is another tutorial on how to calculate the beam deflection. This time we're going to use the direct determination method of the elastic curve from the load distribution. Let's take a look at some basic theory. First we need to take a look at the relations between load and shear. Let's consider the simply supported beam AB shown in the figure, and we say that it's carrying a distributed load W per unit length, and let C and C prime to be 2 points of the beam at distance delta x from each other. So we'll take this segment of the beam, the segment C, C prime. If we detach this portion of the beam of this segment, we will try to draw the free body diagram for it, and it looks like the one shown in the figure right here. The shear and bending at C will be denoted by V and M. These are the values of V and M, and we'll assume this is the positive direction. For now, I mean. The shear and bending moment at C prime will be denoted by V plus delta V and M plus delta M, which is this part right here. The forces exerted on the free body include a load of magnitude Wx. That's if we concentrate this segment of the load, we have to say it's W, the value of the load, and times the delta x, which is the length where the load is distributed. Okay, now if we write the sum of the vertical components of the forces acting on this free body and set it to 0, we will have V minus V plus delta V minus W delta x, that should equal to 0. From that we get that delta V equals minus W delta x. So if I divide both members of the equations by delta x and then let delta x approaches 0, I will obtain dV over dx equals minus W. So what does this thing mean? The above equation indicates that for a beam loaded as shown in the figure, that's the beam we had before, the slope dV dx, which is this equation, of the shear curve is negative. Okay? And the numerical value of the slope at any point is equal to the load per unit length at that point. Again, for a beam loaded shown in the figure, the slope, that's this equation, of the shear curve is negative because of this negative, and the numerical value of the slope is equal to the load per unit length at that point. We'll take a look at the relation between the shear and the bending moment. Okay, I'm going to use the same free body diagram. Using the same free body diagram, now I will sum the moments about point C prime. So, summation of the moments about C prime equals to 0. So first, this is moment which is M plus delta M minus M, then minus V times delta X, then plus W delta X times the distance 1/2 delta X. And if I simplify this, I will have delta M equals V delta X minus 1/2 W delta X squared. Now, if I divide both members of the equation by delta X, then letting delta X approaches 0, you will see that this part will disappear because delta X is going to approach 0 is very small value. Then when you square this small value, it's gonna get even smaller, so this part is approximately 0. So what I'll end up having is dm over dx, so the derivative of the moment diagram is equal to the shear. Basically, that's what this equation is telling me. This equation indicates that the slope dm over dx of the bending moment curve is equal to the value of the shear. This is true at any point where the shear has a well-defined value, i.e. at any point where no concentrated load is applied. So again, the slope dm over dx of the bending moment diagram is equal to the shear. So if I have an equation for the moment diagram, if I differentiate this equation, I will get the equation for the shear diagram. This equation also shows that V equals to 0 at points where M is maximum. That's from calculus. This property facilitates the determination of the points where the beam is likely to fail under bending. Now we jump into the main topic after this brief introduction: direct determination of the elastic curve from load distribution. From previous tutorial, we know that the equation of the elastic curve can be obtained by double integration of the differential equation we discussed in previous tutorial. Okay, so if I double integrate this, I will end up having y equals something. Now my question is, what happens if you differentiate both sides of the above equation? So I will take this equation and differentiate it once, then twice. First, if I differentiate this equation, I will have the third derivative with respect to x equals 1 over ei dm dx, but dm over dx is v. Then the third derivative is just v over ei. Now what if I differentiate it one more time? The fourth derivative with respect to x is equals 1 over ei dv over dx, but we just saw that dv over dx is nothing but minus w. Then the fourth derivative with respect to x equals to minus w x ei. So we conclude that when a prismatic beam supports a distributed load wx, its elastic curve is governed by the fourth order linear differential equation. That's the linear differential equation. Or ei fourth derivative with respect to x equals minus wx. So if we have a beam looks like this, if we know the equation of w, we can get the equation of the elastic curve. And this is another example. See how complicated can the w be? But if we work in a system, we can get the equation of the elastic curve. Okay, so our strategy is as follows. First, get this distributed load equation. Make sure you have an equation for wx. Integrate the distributed load equation 4 times. Apply boundary conditions to find integration constants. Okay, so this is an overlook of the equations you can get. If you have the equation of wx, if you integrate it once, you're gonna get vx, and you'll have a constant of integration c1. Then if you integrate it again, you'll have mx. You'll have a second constant of integration. Then if you integrate it one more time, you will have the slope equation. That will add a third constant of integration, and for the fourth time you will have y of x, and you'll have 4 constants of integration. Let's take a look at the example, and hopefully that's gonna clear out. This is the beam I'm gonna work with. For the beam and loading shown in the figure, express the magnitude of and location of the maximum deflection in terms of W, L, E, and I. Second, calculate the value of this maximum deflection, assuming W is this, L is this, E is this, and I is this. So let's take a look at the solution. To start, we need to write the fourth order linear differential equation EI fourth derivative with respect to x equals minus wx. So what is the equation of wx? If we look at the beam, we can see that it will have an equation of WLx, W over L times x. Let's check it out. If x is 0, of course W is 0. If x equals L, so L will cancel with L and we'll have W, and the minus sign comes from the derivation we just did. Okay, so my first thing to do is integrate it once. What do I have? The third derivative is nothing but the shear equation, and if I integrate this, I will have this, and now I have a new constant C1. One more integration, I'm gonna get the moment equation, and I will have a new constant. One more integration, I'm gonna get the slope or rotation, and I will add another constant of integration. And finally, if I want to get to the elastic curve, or I can the equation where I can get the deflection, I'm gonna get, of course, all of this. Now I'm gonna get the fourth constant of integration. Boundary conditions. So we have 4 constants of integration, so we need 4 boundary conditions. Let's see, what do we have here? This is the beam. First boundary condition, at x equals 0, that's at this support, y equals 0. There is no deflection. Okay, reasonable. Now the second, at x equals L, y is also 0, because it's another support. This support and this support, they do not move up and down under this loading. So these are 2 boundary conditions, 2 more to go. Now, at x equals 0, m equals 0, of course, because at this kind of supports, there is no moment. If the beam, of course, is simply supported like this. And at x equals L, m is as well as equals to 0. So that's a total of 4 boundary conditions. With these boundary conditions, now we will be able to solve for the constants C1 to C4. Okay, let's apply them. At x equals to 0, m equals to 0. So I go to the m equation and substitute x equals to 0 in this equation. I'll end up having C2 equals to 0. That's nice, because now whenever I have C2 in any other equation, I just take it out of the equation, makes the equation simpler. At x equals to L, m equals to 0. Again, in the same equation, because I'm dealing with the moment, I'm gonna substitute for x, I'm gonna substitute L for x, and I will get this equation. Then if I solve for C1, I'm gonna get WL over 6. Now for the x equals 0, y equals to 0, this is the equation for the y, where I will substitute x equals to 0. If I substitute x equals to 0, I will end up having C4 equals to 0. And for the last boundary condition, when x equals to L, y equals to 0. So I go to the same equation, and now I substitute 0 equals, or I'll take out all the x's and put l's and equate this to 0. And if I solve this, I'll end up having C3 equals minus 7 over 360 WL cubed. Now let's substitute them back into the equations. The equation for the shear is this, and simplifying it will look like this. Now the equation for the moment is this, and simplifying it will look like that. The equation of the theta is this. All these equations I'm talking about, this is after the substitution of the constants, of course. and yeah, I took it one more step here. And then for the EIYX, it's this with direct substitution of the constants, but this is after the simplification. I will even simplify them more so they will look nicer. So now also for V of X by itself, so it's gonna be W over 6 LEI times this, and MX gonna be this, theta X gonna be that, and Y of X is this. Okay, now we have these equations. Let's take a look at the maximum deflection. Remember, from calculus, the maximum value of a function is at where its derivative is 0. So, for deflection to be maximum, the slope, or dy dx, should be 0. And we know that dy dx is nothing but the slope theta. So what I do, I take the equation of the theta and equate it or make it equal to 0. Of course, this part cannot be 0, which means that this part can be 0 or should be 0. We need to solve this. I just rearrange the terms so it will look something you've seen before. The solution, it's a standard quadratic equation, but now it's not that standard because we have an x to the 4. I will explain how to go behind this. This is the standard and this is the solution for it. Now this is what we have. This is the solution. See what I did here, I just said x to the 4 is nothing but x squared squared. So x to the 4 minus bx squared plus c is nothing but a, and this x squared I assume to be big X, and this x squared of course is big X. So this form ax squared minus bx plus c will look like this. Okay, now the solution, this is the solution, and this is if we apply the b, a and c, I will end up having x, big X, equals 0.2697 L squared, but I'm solving for small x, which is the square root of this value, and that will give me 0.5193 L. So the maximum deflection is located at the distance x equals 0.5193 L, of course from the left, since I'm taking the x equals to 0 at the left support. Now substituting back into the deflection equation, into this, I'll take all the x's and put 0.5193 L, and if I simplify this, I will have something that looks like this: y max of x equals minus 0.00652 WL to the 4 over EI. Now for part B, calculate the value of the maximum deflection, assuming that the W is 4.5 kips per foot, L is 18 feet, E is 29 times 10 to the 6 psi, and I is 800 inch to the 4. So this is W, and this is L, and this is E, and of course the moment of inertia I. Y max equals negative 0.00652 WL to the 4 over EI. This is what we got. Now all I have to do is just substitute these values and making sure I am using the correct units. Like for this one, the W is in kips per foot, but I convert that to pound per inch. And for the length, I convert this to inches. So I need the forces all in pounds and the lengths all in inches. That will this way I'll make sure that my units are correct. And if I do this, I'm gonna get a Y max of negative 0.229 inches, or 0.229 inches downwards. So this is the example, and it's very systematic. All you need to take care about here is doing it slowly, so the integration will not be wrong, or you'll not have any mistakes during integration. And think about applying the boundary conditions correctly, of course. And that should do it for this tutorial. I hope you learned something today. Thank you.